Okay, so this is a version of the periodic table that I'm going to expect you to know by next week. So we're going to start with a grid, an empty grid of the periodic table. We have a bunch of numbers written in, which should help you focus on the fact that you can identify the position, any position on the periodic table, based on the group number and the period number. So if I say group number 8, period 4, that's one specific box. So that helps you zero in on a number. It's like kind of a Cartesian coordinate system if you look at it that way. But each group number is also called a family, and the families of elements have similar characteristics, so hence the name family. So for example, the first group is the alkali metals. And we can memorize the symbols. We'll start by memorizing all the symbols. There's 112 symbols I want you to memorize. Alkali metals is H, Li, Nac, rubidium, cesium, francium. These are called the alkali, I'll put it over here, alkali metals. Group 2 is also a group of metals, and we memorize it by saying Bemka, Cerbera, Bemka, Cerbera, and they are called the alkaline earth metals. Next week I'm going to be very strict on the spelling. Since we've been doing this since September, you should know how to spell them correctly. The third group doesn't have a name, but I want you to memorize it anyway because it's representing where the break took place that removed F block. This group down here is called the lanthanides and the actinides. They're rare earth metals. So the periodic table was basically cut over here, and that whole piece was removed and put over here so that it wouldn't be too hard to put on one sheet of paper. And if you memorize the atomic numbers of these elements, it allows you to write all the atomic numbers of every single element. So we'll stop there for a moment and we'll go to the other side to the noble gases. Let's write in the numbers. So 3 to 12 is the transition elements. They're all metals. No, actually they're all metals. And you can see where the metal line is. Here's the stair-step line that splits the table into 3 distinct pieces. Metals, metalloids. Here's the metals. They're all this side. The non-metals are on that side, and the metalloids are here, and I expect you to write something like that on the test. Everything that sits on the staircase is a metalloid. Everything that touches the bottom of the staircase is a metalloid, except for aluminum, and I think polonium is here. Well, we'll find out soon enough. I think polonium is here. So we have noble gases: heme, Archer, Zern. This table, this part is empty. These are the noble gases. Noble gases are known for their lack of reactivity. They can be forced to form compounds, but typically they don't. This group is called the halogens, FCl briat. FCl briat is how I memorized it. Halogens. They typically take on a charge of -1. Noble gases don't like to take on charges, so we're going to write a 0 for the typical charge. The next group is the chalcogens, A, Se, Tempo. I put the polonium too low. And they're called chalcogens, probably the most frequently misspelled group name because people forget to put the C. So they write chalogens, but it's not actually chalcogens. They take on typically a -2 charge. Next to that, we have napacib. It's the nitrogen group. It's not a very imaginative name, but that's what they've called it, nitrogen group. And the nitrogen group takes on typically a -3 charge. Carbon, silicon, Gezenpub. Carbon, silicon, Gezenpub is group 14. It also is called the carbon group. Not a very imaginative name either. Same with the boron group. They just took the name for these three. They just named it after the top element. And for the boron group, it's Bal-Gaintal. They take on +3 and +4. With the exception of carbon, carbon has, it's variable. It can take on a +4 all the way down to a -4 oxidation state, depending on what you combine it with. So carbon is probably the most versatile element. It also likes to form long chains. That's why it forms the basis of organic chemistry. It's the backbone of every living organism. It's composed mostly of carbon compounds because of that variability in oxidation states. Then, to memorize across the period, we go through the whole periodic table, turning it into one big word. Sounds funny, but it helps you remember the whole thing. If you memorize in two different directions, you can corroborate to make sure you haven't missed anything or misplaced anything. So it goes Heli Bebkanov, Nina Magalsipsko, Arkask, Tiv, Kerr, Men, Fi, Ko, Nai, Q, Zen, Gajasberger, Herbsri, Zerb, Mott, Ruhr. I also have a little bit of trouble here. Over here, yeah. Padag, Kadinsen Sibteksa. Then it goes Cis, Bala, Half, or Hafnium, Ta, Rios, Erpt, Au, Har. Okay, now you've already got this part done, so that completes it up to period 6. The last line, period 7, going across, Freyak, Rif, Dib, Sig, Ba for borium, Hus for hastium, Mut for meitnerium, Dis, Rig, Cn for copernicium. That's the last one I've memorized. I think there's one more here. I think livermorium or somewhere in there. Maybe next year I'll start teaching that too. That's what I want you to memorize up to. And I want you to know where the atomic numbers go. Of course, it's like writing a paragraph. 1, 2, what does the atomic number mean? It means the number of protons that are in the element. Oh, the charges, right. Charges are +1 here, +2, and +3 for these ones typically. We're going to do the lanthanides and actinides in a minute. Okay, 3 to 12 is called the transition metals. I didn't break that in here. I wrote over there, but it bears repeating. So we lump all of these, this whole group from 3 to 12, we lump it all as one group because the properties are variable in here. You have elements sometimes that even are capable of favoring 1 or 2 charges. For example, copper likes +1 or +2 charges. So they even have a naming system where the higher charge ends in -ik, the lower charge ends in -us. So for example, copper +1 is called cuprous, copper +2 is called cupric. And the OUS or the IC ending is used according to which charge the element will take when it forms an ion. And there are some elements that will even have other oxidation charges. They won't actually form an ion with that charge, but when they're complex with some other element, they can achieve oxidation states as high as +7 in the case, for example, of manganese. I think chromium goes up to +6 and so on. So continuing, period 6, the part that was broken off. Oh, I wasn't finished with the atomic numbers. Remember, the atomic numbers tell you how many protons are in the nucleus of the atom. So hydrogen is the first element. It's only got 1 proton. And incidentally, hydrogen is the only element in which the isotopes have individual names. You've heard of deuterium, and you've heard of tritium, maybe. Deuterium has still 1 proton, but its molar mass is 2. Sorry, 2, because it has a neutron as well. And tritium has a molar mass of 3, because it's got 2 neutrons. And as it turns out, tritium is also radioactive. So the only element that has 3 different names for each one of the 3 isotopes that exist is hydrogen. The other elements, they don't have that. They haven't bothered giving them names, individual names. Lithium is 3, beryllium has 4 protons, boron has 5, so 6, 7, 8, 9, 10. 11, 12, all the way. So I'll expect you to do, you don't have to write out every single number. All I really want you to know is the numbers for lanthanum and actinium, and 5789. Okay, and then you know that it continues in there into the F block, so lanthanum goes, and then after lanthanum you have 58, 59, 60, 61, 62, 63, all the way to 71, and then it continues with 72 for hafnium. Just double check so I don't lead you down the garden path. Rutherfordium is 104. This is 90. This ends at 103. And then you go right to the end, and it'll end at copernicium with 113 or 112. No, it's 112. 112 for copernicium, which means it has 112 protons in its nucleus. And if it's neutral, it'll also have 112 electrons. So we've covered symbols, atomic numbers, periods, groups, all the way from 1 to 18. The sections, there's 3 sections: metals, metalloids, nonmetals. Period names. This period is called the lanthanides, goes across. This period name is actinides. You're going to be asked about the metalloids. You're going to be asked to write a little X into the metalloid boxes. So here are all the metalloids. These two, remember, are not metalloids. The trick for remembering which ones are metalloids, they're sitting on the step or they're touching the bottom of the step. If they're touching a corner of the step, they're not metalloids. So tin is not a metalloid. Phosphorus is not a metalloid. It's only touching the corner of the step. So only the ones that are actually sitting on the step or touching the bottom of the step, with the exception of aluminum and polonium, although some sources will argue that polonium does possess properties that make it resemble a metalloid. So this is arguable, but for the purposes of our test, we're going to say polonium is a metal. Typically, metals all have positive charges. There's only one metal that can accommodate a negative charge, and that is rhenium. It's the only element that is capable, as far as I know, to accommodate a negative charge, which is interesting. The diatomic elements, you should know, there's a mnemonic for it, Hofbrinkel, but it also happens to occupy this number 7 shaped pattern on the periodic table. Astatine arguably is a diatomic, although you never find any astatine on the Earth because it's radioactive. But if you could find it, it would probably be diatomic. So I'll expect you to list it as a diatomic element. Hydrogen is also diatomic, sort of off by itself in the corner. All the group names we've listed, period names are listed, blocks. This section here is the S block. Getting a little bit messy. This whole section here is called the P block because it represents the filling of the p orbitals. All the elements in here are P1, P2, P3, P4, P5, P6. And incidentally, P6 is a very stable configuration. Whenever elements form ions, they will typically adopt the P6 configuration. It's the most stable configuration. This is called the F block. These two strips over here, F block, because it represents the filling of F orbitals. And the last one I didn't put in yet is the d orbitals, which are being filled in the transition metals. We also have to list the usual charges, which we did over here. And then the next thing is the shell filling mnemonic. If you could repoint the camera, because we're going to write it on this board. The shell filling mnemonic, I ask you to write the numbers 1 through 8. And then skip the first 2 and write 2, 3, 4, 5, 6, 7. Skip 2 and start writing one number less than the column below, 3, 4, 5, 6. Skip these 2, write one number less, and then the whole bottom row is S's. Second row is P's. Third row is D, and the last top row is F. And you draw arrows from the bottom of one column to the top of the next one, and that is how the electrons pile in around the atom. Typically, there are obviously exceptions to the rule, and there also are no 8s orbitals. I just wrote in the 8s there to complete the pattern, otherwise you get this, and it tends to cause confusion. So I filled the wedge in. If you had an 8s1 atom, it would appear over here in a hypothetical group 8, group 1, period 8. There is no such element, but it helps to preserve the pattern. And then I'm going to ask you, and I'll tell you right off the bat, I'm going to ask you to give me the configuration of uranium. Uranium, if you can fill out the table, what you'll find out has 92 protons. Oh, and I forgot to do the elements for the bottom row, so I'll do that first. There's a mnemonic for that too. It goes Chepern, Pimsim, Ugad, Tibdi, Ho'er, Pimib, Lu. Say it fast. Chepern, Pimsim, Ugad, Tibdi, Ho'er, Pimib, Lu. You say it fast, it tends to stick better. I don't know why. Maybe we remember the sound, and then when we reproduce the sound, we can retrieve what letters to write for it. It makes it easier. The more you compact the information, the easier it is to remember. You don't have to do it the way I do it, but this is what I recommend. So uranium, here we haven't done uranium yet. The second of the actinides is the pon. You can think of Arnold saying the pomp. Puam, pompuam, come back. Kafes, efemd, nolar. All right, the pompuam, come back, kafes, efemd, nolar. Uranium is here. It's got 92 protons. 92 protons, so we have to account for it when we draw. Yeah, I'll have to repoint the camera maybe. 92 protons following the pattern. I forgot to mention that in S block you have a maximum of 2 electrons. In P you're going to have a maximum of 6. In D it's going to be a maximum of 10. And in F it's a maximum of 14. So when you fill in when you do the shell filling mnemonic, you go through each orbital and you put in the maximum number of electrons that it can hold until you get 92 electrons. And as you approach the element that your target element, you're going to look at what period it's in. So it's in period 7. So as soon as you get to radium, which is going to be S2, 7S2, you know that you're getting close to finding the configuration of uranium. And then you can also count up the electrons to make sure you have the correct number. So it's going to go 1s2, 2s2, 2p6, 3s2. See, all I'm doing is writing the next orbital and then filling it up with the maximum number of electrons that it can hold, because the electrons all fall down to the lowest level. So it's like you're filling up a cup of water. It fills from the bottom up to the top. You never see the water stay at the top and then filling the bottom first. So electrons do the same thing. They fall to the lowest energy levels, and then they fill up the atom accordingly. So we're up to 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Where are we now? We're at 5s2 is here, strontium. So we still have a ways to go. 5s2, 4d10, 5p6, 6s2. I'm running out of room, so I'm just going to start over here. 4f14. So I fill the whole F block on the lanthanides, but I'm going to have to go up to here on the actinides. 4f14. That brings me here. 5d6. That's going to be filled. 6p10, 7s2. I'm now up to radium, and 5f. Let's count in how many. 1, 2, 3. Now, of course, when you get into F block, you have to look at some variations in there. Double check. I predict 5f3, and it says here 5f3, 6d1, 7s2. So there's a slight 61. Yeah, there's a slight variation there for the 6d orbital. One of them goes into the 6d orbital. Perhaps not a good example for somebody who's starting out to do these things. But you'll find that sometimes it doesn't exactly follow the pattern. In the case of uranium, unfortunately for our example, one electron goes into 6d1. And if you count them all up, it adds up to 92. I also want you to be able to write the shorthand version of uranium. You can do that by writing a square bracket around the closest noble gas that resembles uranium, which would be radon. And I believe radon has 86 protons. So you write square bracket, radon, and then fill in the rest of the shell. Remember, they're all end in 6p. Oh boy, I got something wrong here. 4f14, 5b10, 6p6. Sorry about that. I didn't do that anywhere else, did I? Yeah, okay. So it ends radon, 7s2, 5f3, 6d1. That's the shorthand version for uranium. See, this up to here would be the configuration of radon. So all you're doing is writing a square bracket to represent everything up to that point, and then the remainder you write out. That's the shorthand version. The next question you're going to be asked is to rank a set of ions according to size. Okay, so let's give you a set of isoelectronic ions. Let's take, for example, phosphide, sulfide, chloride, argon, potassium, and calcium. The question will be something like, rank these according to size. And I'm going to give you a set of isoelectronic ions, meaning that the ions have exactly the same number of electrons, all of them. So phosphide, sulfide, chloride, argon, potassium with a plus charge, calcium with a +2 charge, and say scandium with a +3 charge. All of these have the same number of electrons. They all have the same number of electrons as argon, which is 18. You write the electron configuration for all of these, from phosphide all the way up to scandium +3. They all have 18 electrons. They'll be 3p6. They'll end in 3p6. They all end in 3p6. They all have the same number of electrons, but they have varying numbers of protons. This one's got 15, 16, 17 protons, 18 protons, 19 protons, 20 protons, and 21 protons. So what's that going to do to the size of the element? Well, the one that has the most protons is going to pull those electrons, those 18 electrons, closer to itself, whereas the one that's only got 15 protons is going to let them be further away. So this is going to be the biggest one, and this is going to be the smallest. So really all you have to do is put greater than symbols in between all of them, pointing to the right in this case. The biggest atom here is the phosphide anion, and the smallest one is the scandium cation. Then I ask you to explain the ranking. So in your own words, you will say something like, the atoms with more protons pull the electrons closer, which makes them smaller. So I'm oversimplifying. Obviously, you'll use a bit more. You'll use a bit more detail when you explain it. I'm just doing it for the sake of brevity, but that's the gist of it. The atoms that have more protons will pull the electrons closer and it'll make them smaller. The next question I ask you in this test will be Lewis structures, and I picked nitrate and nitrite. nitrate and nitrite. There's a trick to drawing Lewis structures. What you do is you list all the atoms involved. So you're going to make a little T-chart. Atom, number of valence electrons. You have two atoms in nitrate, nitrogen and oxygen. And based on where they appear in the periodic table, nitrogen appears in group 15, so that means it's got 5 valence electrons. Oxygen appears in group 16, so it's got 6 valence electrons. Just look at the second number and the group number, it'll tell you how many valence electrons it has. Nitrate has 3 oxygens, so you're going to say 6 times 3 for the number of electrons, and it's got that extra minus charge, so we're going to add a plus, we're going to add 1 extra electron. By the way, when you draw a Lewis structure, if you don't get an even number of electrons, you have a radical. So it's an unstable molecule. You always are going to get an even number of electrons. Always, always, always. Okay, so if you don't get an even number of electrons, you've done something wrong for the purposes of a grade 11 course. Don't start drawing a Lewis structure with an odd number of electrons unless it happens to be something like ozone. Ozone will probably have an odd number of electrons because it's an unstable molecule. So this is 18 plus 6, 24 electrons have to appear in the nitrate anion. So you begin by picking your central atom, which is nitrogen, and then connecting oxygen atoms to it. That already uses up 4 electrons, 2, 4. And then disperse the remaining 20 on, whoops, I forgot one atom. There we go. So it's 6 electrons used up. So now you have 18 electrons to disperse. So let's disperse them around the oxygen atoms and see what that gives us. The way I've drawn it now, first of all, nitrogen doesn't have a complete octet. It wants to have at least 8 electrons somewhere around it, either in the form of bonds or non-bonding electron pairs. But you see here that there's only 6 electrons. So what we're going to do is, well, we're going to modify the structure, but first let's account for what the charges are going to be like. Oxygen likes to have 6 electrons around it, no matter what. But you see here that it's got 2, 4, 6 plus the 1 from the bonding pair. So this one's got 7, giving it a minus charge. This will do the same. This will have a minus charge. And this nitrogen, the way we've drawn it, is deficient in 2 electrons. So because they only count for 1 when you account for charges. For octet considerations, the bond, you actually count this as 2. So we have 2, 4, 6. So it's deficient on the octet, and it's deficient in the charge consideration. So this nitrogen atom has a plus 2 charge. Overall, the molecule would be minus 1, which would be accurate for nitrate. But let's modify the structure to fulfill the octet consideration. So we'll do that. And what we get is this double bonded, and these oxygen atoms be minus 1, minus 1. This nitrogen will still be plus 1, so you'll still have some formal charges, but now you've minimized the number of formal charges, and nitrogen has a full octet, and so do all the other oxygen atoms. See, we have 2, 4, 6, 8 on this oxygen atom, 2, 4, 6, 8 on that one, 2, 4, 6, 8 on that one. When you count for charges, the bonds count for 1, so it's 2, 4, 6 plus 1 gives you 7, therefore you get a minus charge on the oxygen because it only wants 6. Same here, it's got 7, it only wants 6, therefore this has a minus charge. Overall, this whole molecule is minus 1 because the minus and the plus here counterbalance. And of course, the double bond can vary in its positions. This is the nitrate anion. The nitrite will look like this. First, we can account for how many valence electrons are in the molecule. So NO, number of electrons, is 5 for nitrogen, 6 for oxygen, of which there are 2 in nitrite, and then 1 extra electron for the charge. So that's 12 plus 6. 18 electrons have to be accounted for in the Lewis structure of nitrite. And so we're going to start by drawing your oxygen atoms. That uses up 4 electrons, so that means we still have to disperse 14. 2, 4, 6, 8, 10, 12 The last two go on the central atom. The way we've drawn it, there's not a complete octet. The nitrogen has a plus charge, this has a minus, and that has a minus. So we can modify the structure by taking one of the lone pairs and turning them into a bonding pair. And this is what we get as a viable Lewis structure. Still a -1 charge over here. And no other charges, no other formal charges. See that nitrogen has 2, 4, 6, 8. It's got a full octet. And for charge, we count these ones, the bonds for 1, so 1, 2, 3, plus the 2, 5. It's got possession of 5 electrons, therefore no charge on the nitrogen, and no charge on this oxygen, and it also has a fulfilled octet, 2, 4, 6, 8. Okay? So that's the Lewis structure I expect you to be able to draw for next week's test. I'm also going to expect you to know the names of polyatomic ions. So what does that mean? I expect you to know it two ways. If I give you the name of the polyatomic ion, I want you to be able to draw the structure as it appears on the flashcards that I made for you. Or if I give you the structure, I expect you to name the ion. So just as an example, if I say chlorate, you'll draw ClO3-. That's what chlorate looks like. If I say perbromate, you're going to say BrO4-. If I say iodide, you're going to draw me the iodide ion. The other way around, if I draw you permanganate, then you can name it, and you have to spell it correctly as well, permanganate. If you make a spelling mistake, it's going to mark it wrong. Bisulfate. You can also say hydrogen sulfate, that would be valid. If I draw you this, you'll say hydrogen phosphate. So these ones it's just sheer memorization, I'm afraid. But there is a method to memorize these polyatomic ions so that it's less work, and I've shown you how to do that. The next thing I will expect you to know is the trends in the periodic table. I'm going to ask you about the ionization energies. Ionization energies which is the amount of energy it takes to remove one electron from a gaseous atom. They tend to increase as you go up the periodic table, and it increases as you go to the right. So the atom, theoretically, that's hardest to take an electron away from is probably around fluorine, towards the top right of the periodic table. Whereas the atom that is easiest to take an electron away from would be francium or cesium. And it stands to reason because with metals, the outer last shell, the valence shell of electrons is shielded by a whole bunch of electrons in between, and it's further away from the nucleus, so it's easiest to take away those electrons. Also, the atomic radii. Atomic radii means the size of the atom tend to decrease as you go across the periodic table, and okay, so they increase when you go this way and when you go to the bottom. Or the way I like to remind you is, think of my hand closing as I go to the right. So the atoms get smaller as you go across the table, and they get bigger as you go down. As you get more electrons, obviously you have to get more shells. So I want you to know those two trends. I want you to know the electronegativity series. What is the electronegativity series? It is a measure of how much attraction an atom has for the electrons when it's in a bond. And this is not an exhaustive list, but von Kohlberg metals. Fluorine is the most electronegative element. Metals are the least electronegative element. Hydrogen is sort of in the middle. If you pair a hydrogen atom with any of these guys, then the hydrogen will act positive. If you pair hydrogen with any metal, the hydrogen will be negative. It will actually take the electrons away from the metal. I also want you to know the activity series. The activity series allows you to predict whether an atom will give its electrons to another atom. If an element is higher up on the activity series, it will push its electrons onto another atom which is below it on the activity series. And this is how we memorize the activity series. Lik, ba, ka, na, magal, min, zinker, hyponycin, PBH, QAG, UG, Tau. Lithium has the highest oxidation potential and is most likely to give electrons to any atom below it, and gold is the least reactive and the least likely to give away electrons to another atom. So any element that's on this end of the activity series tends to be quite unreactive by comparison to the ones up here. And in a single displacement reaction, you will see that these ones will donate electrons to other metals lower on the activity series. I expect you to know the strong acids by heart, and there's a trick for memorizing that. It goes no, so, claw, coal, breathe. Put hydrogen in front of each one. And it goes 3, 4, 3, 4. Nitric, sulfuric, chloric, perchloric, hydrochloric, hydrobromic, hydroiodic acid. Only one of them has 2 hydrogens. All the other ones are monoprotic. Strong bases. Nacurb, Cassarba. These ones have 1 OH group in front of them. These ones have 2 OH groups in front of them. These are group 1 metals, but not all of them. And these are group 2 metals, but not all of the group 2 metals. Okay, so Nacurb, Cassarba, those are all strong bases. If it's not a strong base, it's a weak base. If it's not a strong acid, it's a weak acid. I know it sounds kind of trite, but that's what it is. Then I want you to show how to balance an equation, as well as to give the molecular, the ionic, and the net ionic form of the reaction. And I'll give you an example of what I'm going to ask you in the test. I say in the question, and I think it's question number 11, show the balanced molecular, ionic, and net ionic reaction, equations for the reaction of silver nitrate with potassium chloride. So I'm just going to write the words. I'm not going to give you any formulas. You have to get the formulas out of your own head. You have to balance them. So this is not as easy as it might look at first glance. So the first thing is you write down what's reacting. Silver nitrate is reacting with potassium chloride. So we'll draw the molecular equation first. So silver nitrate, which is aqueous, is reacting with potassium chloride, which is also aqueous. You're going to get silver chloride and potassium nitrate. This will be the one solid product. And if you look up the solubility tables, you see that chlorides are very insoluble if they're silver chlorides. The next step is to show the ionic equation, in which you show everything that is dissociated in its dissociated form. So silver will be the silver cation, nitrate will be nitrate anion, potassium will be a cation, and chloride will be the anion. But of course, the silver chloride forms a precipitate. This stays in aqueous form. And then when you look at the ionic equation, you'll see that you'll get a repetition of some of the ions. Those are called spectators, means they don't participate in the reaction. So what you do is you cross them out and you don't write them in the, oops, cross this one out, should have done that. The nitrate and the potassium cross up because they just stay in solution. They don't form a precipitate, they just float around, they're spectators. So in the net ionic equation, you don't include the spectator ions. What you write is only the things that are reacting. So Ag plus cation plus the chloride anion are combining to form silver chloride, which then precipitates out of solution. So this is three different ways of representing the same chemical reaction, each one with its particular purpose. And lastly, I want you to do a conversion. In this particular test, I'm going to ask you to convert 3 feet cubed into nanometers. How many nanometers is that? Remember, nanometers is billionths of a meter. But remember, we're dealing with volume, so these conversion factors are going to have, they'll have to be raised to the power of 3. So here's what we do. We're going to start off with 3 feet cubed times 12 inches per 1 foot. We start off with the linear conversion, but remember that it's a volume measurement, so it goes in 3 dimensions. That's why you raise it to the power of 3. Then we convert to centimeters. There's 2.54 centimeters in a linear inch, but we raise it to the power of 3 because it's a volume measurement, again. Then we go to meters, 1 meter per 100 centimeters. Notice I'm trying to cancel centimeters, so I put centimeters on the bottom. If I write it the other way, I'm going to get the wrong answer. I'm trying to get rid of centimeters to keep meters. Again, raising it to the power of 3. And lastly, we convert to nanometers. There are 10 to the 9 nanometers per 1 meter. And again, we raise it to the power of 3. When you multiply all of that together, it comes out to 8.495 times 10 to the 25 nanometers. Any questions? Okay, send it there.